Okay, guys, let's discuss chemistry past paper 2019, paper 2, May June. So the code is this one, 2.2. Okay, let's start. Question number 1. Methylpropane is an isomer of butane. Explain why methylpropane and butane are a pair of isomers. Okay, so in this case, we know that methylpropane and butane are structural isomerism. They are structural isomers. So they have the same molecular formula. Okay, C4, it's 10. Okay, let's check. 4 carbon atoms with 10 hydrogen atoms. 4 plus 3 plus 3. Okay, so I want to count the total number of hydrogen atoms. 2 times 2, 4 plus 3 plus 3. Okay, 10. So 4 carbon atoms with 10 hydrogen atoms. Okay, if you check, it has the same molecular formula. So they have the same molecular formula but different structural formula. Butane is straight chain while methylpropane is branch chain. Okay, so if you draw the structural formula, this is the structural formula of butane, straight chain without branch, while for methylpropane, CH3, CH3, and CH3. There are two methyls here, so CH3, CH3, CH, CH3. Okay, so the chain consists of branch or alkyl. So butane is straight chain while methylpropane is branch chain. So we can answer this question. Explain why methylpropane and butane are a pair of isomers because they have because they have the same molecular formula but different structural formula. When they have different structural formula, they also have different name. Okay, next. Identify the type of isomerism shown by methylpropane and butane. As I told you, the type of isomerism is structural or chain isomerism. Remember, there are three types of structural isomerism: chain, position, and functional group. Okay, in this case, you may answer structural or chain isomerism because they have the same molecular formula but different structure of carbon skeleton. One is straight chain and the other one is branch chain. Okay, next. So this question is about equilibrium. State and explain the effect on the composition of this equilibrium mixture when the temperature is increased to this temperature. So the temperature increases. So what happened to the equilibrium? So you have to answer this question based on Le Chatelier's principle. When temperature increases, the equilibrium shifts to the endothermic reaction, or the site that needs energy or heat. Okay, so remember once again, when temperature increases, the equilibrium shifts to the site that absorbs or need energy or heat, or endothermic reaction. Okay, since the forward reaction is exothermic, the forward reaction is exothermic because the sign of enthalpy change is negative, so the reverse reaction is endothermic. So in this case, the equilibrium shifts to the left. Okay, so you have to mention the reason, you have to state the reason. Since the forward reaction since the forward reaction wait since the forward reaction is exothermic, okay, the equilibrium shifts to the left since the forward reaction is exothermic. Shifts to the left, so more reactant will be produced. Okay, so more butane, more butane, more butane will be produced. Okay. Next. Okay. 1 mole of butane gas was added to 1 liter's closed system at a constant temperature and pressure. The amount of butane and methylpropane was measured at regular time intervals. So there is a graph, time versus amount in mole. Remember, generally the reactant decreases and the product increases. Okay, 1 mole of butane gas was added. Okay, so this 1 mole of butane gas was added. So this line, this graph is for butane. The amount of butane and methylpropane was measured at regular time intervals. Okay, so this graph represents the mole. So this graph represents the rate of reaction or the mole and time of methylpropane. Okay, so once again, 1 mole of butane is added. So this graph is for butane and this graph is for methylpropane. Okay, label the graph with a T to show the time taken to reach dynamic equilibrium. Okay, remember, we have a graph time versus amount in mole, okay? So actually this graph represents rate of reaction. So remember, rate of reaction equals to concentration change per unit time. Okay, so the concentration can be mole, can be concentration in mole per cubic decimeters, gram, volume, and etc. Okay, so actually this graph represents the rate of reaction. Okay, remember when dynamic equilibrium has been reached, so the rate of forward reaction and the rate of reverse reactions are the same, or the rate of forward reaction equals to the rate of reverse reaction. Okay, so the rate must be equal. The rate of forward and the rate of reverse reactions must be the same, or rate of forward reaction equals to the rate of reverse reaction. Okay, so you see horizontal straight line here. The horizontal straight line here represents the equilibrium has been reached. Okay, so the horizontal straight line, once again, there is horizontal straight line here. It represents that equilibrium has been reached. Okay, but you have to label the graph with a T to show the time taken to reach dynamic equilibrium. So the first point when the equilibrium has been reached, okay, so it's about this one. Okay, so this one. Okay, wait. Okay, so it's about this one. So you have to use ruler. Okay. Okay, so you have to label the graph with a T. Okay, so the first point when the equilibrium has been reached, so it's about this one. Okay, next. Use the graph to find the concentration of butane and methyl propane in the mixture at equilibrium. The concentration of butane, okay, the concentration of butane at equilibrium. Okay, so just look at the horizontal straight line and you make a line, make a horizontal line, this one, and then you can find that the concentration of butane, oh sorry, so this is the concentration of methyl propane at equilibrium, right? So 0.7, so this is the concentration of methyl propane at equilibrium, 0.7, while the concentration of butane at equilibrium, so this one, see the horizontal straight line here. Okay, so if you make a line, okay, you have to use ruler. Okay, so it's 0.3. Okay, so you have to see the horizontal straight line and you make a horizontal line. Okay, so you make a horizontal straight line until it reaches the y-axis here, okay, and then you flip the number, okay, 0.3 and 0.7. Okay, next, write an expression for Kc for this reaction. Kc equals to concentration of product divided by concentration of reactant. Remember, both of them must be at equilibrium. The concentration of product at equilibrium divided by concentration of reactant at equilibrium to the power of reaction coefficient. Okay, if you see the balanced chemical reaction or equilibrium reaction, it's already balanced and the reaction coefficient is 1. All of them have the same reaction coefficient, 1 1. Okay, so the concentration of product, the product is methyl propane divided by concentration of reactant. The reactant is butane, or you may write the chemical formula, or not the chemical formula because they have the same molecular formula, the structural formula. Okay, that's okay if you want to write the structural formula. Okay, next, calculate the value for Kc and state its unit. Okay, so you have to use this equation to calculate the value for Kc and to find its unit. Kc equals to concentration of methyl propane at equilibrium 0.7 divided by concentration of butane at equilibrium 0.3. Remember, all of them have the same reaction coefficient 1. So to the power of 1 to the power of 1. 7 over 3, so it's 2.3. Okay. Okay, and the unit is there is no unit. Remember, the unit for concentration is mole per cubic decimeters. Mole per cubic decimeters. Okay, so they cancel each other. So there is no unit. Okay. Next. Group 17 elements are commonly referred to as the halogens. State and explain the trend in volatility of chlorine, bromine, iodine down the group. So remember, what is volatility? The ability of substance to evaporate. Okay. As go down the group, group 17 elements have the higher boiling point. So as go down the group 17 elements have higher boiling points, or boiling points increase as go down the group. So the volatility decreases. Okay, the volatility decreases because as go down the group, the boiling point increases. The boiling points increase. Okay, so it's more difficult to evaporate. More heat or more energy is required to break the van der Waals forces. Okay, volatility decreases due to boiling point increase. Why? You have to explain. Remember, for group 17 elements, the boiling point or melting point is affected by intermolecular forces. Halogens are nonpolar. So its melting point or boiling point is affected by van der Waals forces. Okay, so they have stronger van der Waals forces as go down the group. Why? Because they have greater number of electrons. Okay. Stronger van der Waals forces, it means that more energy or heat is required to break these forces. Okay, next. State the conditions required for chlorine to react with hydrogen at room temperature. Okay, so it's similar to the reaction between alkene and halogen. Okay, so the condition required is UV light. UV light is used to break down the bond in halogen. Okay, so yeah, so it's actually it's like a catalyst. On heating, iodine reacts with hydrogen in a reversible reaction. Give the equation for this reaction includes that symbols. Iodine reacts with hydrogen in a reversible reaction, so you have to use double arrows. Okay, the product is hydrogen iodide Hi. It's not balanced yet. 2Hi. With the state symbols, all of them are gases. Okay. Next. Hydrogen chloride reacts with water. In this reaction, one of the reactants behaves as a Bronsted-Lowry acid. What is Bronsted-Lowry acid? Proton donor. In this case, the proton is hydrogen ion or H plus. How about Bronsted-Lowry base? Bronsted-Lowry base is proton acceptor and the proton is H plus or hydrogen ion. Identify the reactant behaving as an acid and its conjugate base. Okay, so look at the reactant. Okay, focus on the reactant first. We want to identify the acid on the reactant. Remember, Bronsted-Lowry acid is proton donor, so it must donate proton. It means that the number of proton decreases, the number of hydrogen decreases after reaction. Okay, so this one, right? And look at the pair. Okay, from HCl to Cl minus. Okay, from HCl to Cl minus, it means that HCl lose one hydrogen ion or one H plus or one proton. Okay, so the acid is hydrochloric acid, hydrogen chloride, and the conjugate base is Cl minus. Okay, chloride ion. Cambridge differentiate between hydrogen chloride and hydrochloric acid. Hydrogen chloride is for gas. Okay, actually hydrogen chloride is for gas while hydrochloric acid is for hydrogen chloride that dissolves in the water and ions are produced. Okay, once again, Cambridge differentiates between hydrogen chloride and hydrochloric acid, but actually they have the same chemical formula, HCl. Okay, but for hydrogen chloride, this term is used for gas, usually gas. Okay, so there is no water here, and hydrochloric acid is for hydrogen chloride dissolved in the water and HCl and Cl minus are produced. Okay, so it's aqueous actually. Okay, because ions are produced in the water, so hydrochloric acid is for aqueous. Okay, so only different term, but they have the same chemical formula. Okay, next, name the type of bond formed between H plus and H2O to make H3O plus. The answer is coordinate or dative covalent bond. Okay, so remember when water reacts with H plus, okay, so I want to draw the Lewis structure of water first, this one. Okay, in this case, oxygen has two lone pairs of electrons on the center of atom and it's reacted with H plus. Okay, hydrogen is stable if it has two valence electrons or two outermost electrons. So in this case, oxygen atom from water donates a lone pair of electron to H plus. Okay, so now okay, so now there is a coordinate covalent or dative bond between oxygen and hydrogen atoms. Okay, coordinate or dative covalent bond. The oxygen atom donates a lone pair of electron to hydrogen, but oxygen doesn't use electron of hydrogen at all. Okay, once again, why coordinate or dative covalent bond is formed? Because in this case, only oxygen donates a lone pair of electron to hydrogen, but oxygen doesn't use any electron from hydrogen because oxygen has been stable. That's coordinate or dative covalent bond. Okay. For common covalent bond, for example, this one, covalent bond between oxygen and hydrogen atoms here and here. Okay, so it's common covalent bond because actually the electron pair is shared between hydrogen and oxygen atoms. The electron pair is used together between hydrogen and oxygen atoms. But for coordinate or dative covalent bond, one of the atoms donate electron pair, lone pair of electron to other atom, but in this case, oxygen atom doesn't use any electron from hydrogen. So oxygen atom only donates lone pair of electron to hydrogen, but oxygen doesn't use any electron from hydrogen. Okay, that's coordinate or dative covalent bond. Next, predict its shape and the bond angle. So for hydroxonium ion, H3O plus, predict its shape and the bond angle. Okay, so we have three covalent bonds here and one lone pair of electrons, so the shape must be trigonal pyramidal. Trigonal pyramidal. Okay, with the bond angle of 107 degree. Okay, actually this is not the actual molecular shape. The actual molecular shape is this one. Okay, so this one. trigonal pyramidal. Okay. Next, number 3. Pair 3 elements react with chlorine gas Cl2 to form chlorides. The table shows the differences in observations which occur when 2 pair 3 chlorides are added to water, sodium chloride and silicon tetrachloride. When they are added to water separately, so for sodium chloride, white solid disappears, colorless solution made, and the pH of solution formed with water is 7, while for silicon tetrachloride, pale yellow solution forms, bubbles form, and the test tube feels hot, white precipitate forms. Okay, and the pH of solution formed with water is 1, it's about 1 to 2. Okay. Okay, next. Write an equation for the reaction occurring when silicon tetrachloride is added to cold water. Include state symbols. Okay, so you have to memorize the equation. Silicon tetrachloride is added to cold water, H2O, to produce silicon dioxide and hydrogen chloride. This is solid. Silicon dioxide, this is solid. White precipitate. The white precipitate is silicon dioxide, while hydrochloric acid is gas. Okay, pale yellow solution forms, bubbles form, and the test tube feels hot. Okay, bubbles form. And this is liquid, cold water, and this is liquid. Okay, now you have to balance the equation. Okay, it's not balanced yet, so 2, 4. Okay, next. Name the type of reaction occurring when silicon tetrachloride is added to water. Ignore the exothermic or endothermic nature of the reaction. Silicon tetrachloride is covalent compound. When it's added to water, there is new substance produced. Okay, once again, silicon tetrachloride is covalent compound. When it's added to water, there is reaction between them and new substance is produced. Okay, this is called hydrolysis. Okay, this is called hydrolysis. Okay, because the covalent compound reacts with water to produce new substance, while for ionic compound, when it's added to water, it only dissolves in the water to produce ions. Okay, so the ionic compound only dissolves in the water and ions are produced. Next, explain in terms of bonding why sodium chloride and silicon tetrachloride behave differently when added to water. Explain in terms of bonding why sodium chloride and silicon tetrachloride behave differently when added to water. As I mentioned before, sodium chloride has ionic bond while silicon tetrachloride has covalent bond. That's why the ionic bond dissolves in the water, only dissolves in the water when it's added to water, while for covalent bond, it's hydrolyzed with water when it's added to water. Okay. Next, explain in terms of electronegativity when the bonding in sodium chloride is different from the bonding in silicon tetrachloride. Okay, once again, explain in terms of electronegativity why the bonding in sodium chloride is different from the bonding in silicon tetrachloride. In terms of electronegativity, so remember, ionic bond always has bigger electronegativity difference than covalent compound. Okay, so once again, ionic bond always has bigger electronegativity difference than covalent compound or covalent bond. Okay, so in this case, we can say that there is big electronegativity difference between sodium and chlorine. There is a big electronegativity difference between sodium and chlorine, while only small electronegativity difference between silicon and chlorine. So the big electronegativity difference between this atom is leading to the formation of ionic bond. Okay, while the small electronegativity difference between these atoms is leading to the formation of covalent bond. Okay, and then you have to explain what is ionic bond. So how is ionic bond formed, or the formation of ionic bond? So there is electron transfer from Na to Cl, while for covalent bond there is electron sharing between silicon and chlorine atoms. Okay. Okay, next. Identify the oxidation number of chlorine in each of the chlorine-containing species in this reaction. So you have to identify the oxidation number for each element. So the oxidation number for chlorine atom in Cl2 is 0, okay? Because this is free element, while oxidation number of chlorine in HCl is -1. Okay, so if you are confused, just split the ionic compound or the covalent compound into ions. It's plus and Cl minus. Okay, so actually this is covalent compound, but when it's added to water, it can produce ions. Okay, so you can identify the ions produced. Okay, and the oxidation number is the same as the charts in this case. Okay, while for this one, okay, I split into ions first. It's plus and ClO minus. Okay, so it contains polyatomic ion. ClO minus is polyatomic ion. Oxidation number of chlorine in this ion is, okay, the oxidation number of oxygen is -2 times 1, so -2 again, minus 2 plus something equals to minus 1. Minus 2 plus something equals to minus 1. The overall is minus 1, so it's minus 1 plus 2 plus 1. Okay. Plus 1 divided by 1 plus 1. Okay, so the answer is plus 1. Name the type of reaction occurring. Okay, so 0. Okay, guys, in this case, the oxidation number of chlorine in Cl2, okay, or we can say the oxidation number or oxidation state of chlorine decreases from decreases from 0 to minus 1, sorry. The oxidation state or oxidation number of chlorine decreases from 0 to minus 1, and at the same time, the oxidation number of chlorine increases from 0 to plus 1. Okay, so at the same time, chlorine gets reduced and oxidized. So it's this proportionation. Okay, once again, the oxidation state or oxidation number of chlorine decreases from 0 to minus 1, and at the same time, the oxidation number or state of chlorine increases from 0 to plus 1. Okay, so the chlorine atom gets reduced and oxidized at the same time. That's called disproportionation. Explain why chlorine is used in the purification of water to kill bacteria or microorganism. Next, a mixture of hydrochloric acid and HClO is added to cold dilute sodium hydroxide. One of the products behaves as a bleach. This is NaClO. Suggest the equation for the reaction occurring. This reaction is similar to the reaction between cold dilute sodium hydroxide and chlorine. Okay, so once again, this reaction is similar to the reaction between cold dilute sodium hydroxide ion and chlorine. Okay, so suggest the equation for the reaction occurring HCl plus HClO plus NaOH produce NaClO plus NaCl plus water. Okay, once again, this reaction is similar to the reaction between cold dilute sodium hydroxide and chlorine. Okay, it's not balanced yet. You have to balance it. 2 and then 2. Okay, please check again. Okay, it's balanced now. Okay, it's done. For question number 4 to 5, I have discussed it on the previous video. Okay, so please let me know if you still don't understand, and we will have Zoom meeting, okay, to discuss about your question. Okay.